All right, so today we have a special guest on. What's your name?
Sebastian?
Is that your real name?
No?
Okay, great. So what we're going to do today is I'm going to ask Sebastian a set of some math questions just for fun, and he's going to ask me some math questions. The only real rule here is that, Sebastian, you have to tell me what you're thinking out loud as you're trying to solve these, and I'm going to do the same.
Okay.
Okay? All right. Do you want to go first? Do you want me to go first? I'll go first.
Okay.
All right. This is just an easy warm-up. What is the meaning of life, the universe, and everything?
42?
How'd you do that?
I don't know. From memory.
Great. You just had it memorized?
Yeah.
All right, great. What's your first question?
59 decillion factorial.
It's a very big number. Today, since this is a V-neck math episode, here's a math joke for you. Two mathematicians are sitting across from a cafe. They see two people go into the cafe. A while later, three people come out of the cafe. The first mathematician turns to the second and says, "You know what this means, don't you?" The second mathematician says, "Yeah. If one more person goes in that cafe, it'll be empty." All right, you ready for your next question?
Yeah.
What is 14 squared?
Wait, I don't know.
Figure it out.
So, I would do 14 times 10 equals 140. 14 times 4 equals 56. And it's 196.
All right. I like the way you broke that down. You want to ask me your next question?
Yeah.
All right.
44 times 9 with x as 9 times x equals 92 million. I mean, like, I would do 44 times 9 and then 92 million divided by that, and then that would be x.
That's exactly what I would do.
Yeah.
Do you want me to do it?
Yeah, sure, if you want.
All right. 40. And then I would check it by doing 44 times 9 times that and see if I got 92 million.
Cool.
You ready for your next question?
Yeah.
How many factors, do you know what factors are?
Yeah.
What are the factors of 4?
2, 1, 4.
Great. Okay, so how many factors does 87 have?
I don't know. I'm not interested in doing it.
Okay.
Well, it's probably an odd number, so yeah, it is.
Why is it an odd number?
Well, prime number.
What's, like 87 is a prime number, or the number of factors is a prime number?
I'm pretty sure 87 is a prime number.
Right. Do you know the trick for knowing if you can divide by a number by 3 or not?
Oh, wait, I can.
What's the trick?
Oh, I meant you can divide by 3
Oh.
and 87.
How do you know?
It's 87 divided by 3.
You did it?
Yeah.
Oh, what'd you get?
Like 29 or something?
Or something?
Yeah.
Okay. So you know some of the factors of 87. How are you going to find all the factors of 87?
I mean, I could do, like, a factor tree, I guess. Like, I'm like...
Don't cheat and look at the other questions now. Yeah, it's a big deal.
87, like, I could do 3. And what I say was, like 29. Yeah. And 87. And 1. 187, 3, and 29.
How do you know there aren't any more?
Well, I mean, 29 divided by, like, 9 is, like, have a decimal at the end.
Okay.
29 divided by 8, yeah. 29 divided by 7, 29 divided by 6, 29 divided by 4, 29, whatever.
Okay. So how many factors does 87 have?
4.
Nailed it.
Yay.
Yay. All right. Do you have another question for me?
Yeah. Final question.
Final question. All right.
Thomas Running invented running in 1874 by trying to walk twice at the same time. if he walked at 3 million times the speed of light in a nanosecond, what day would it be if he were to walk 100 googolplex tenths of a kilometer? He started in January 14th, 2019.
Okay, so first of all, this problem is about the future.
Yeah.
That day hasn't even happened yet. Second,
wait, it hasn't? I thought
no.
it was the 14th.
No, it's the 13th. It's Grandpa's birthday.
Oh, cool.
Yeah.
Good to know.
All right. So also Thomas invented running by trying to walk twice at the same time. Yeah. Is just a great setup. So hold on. He walked at 3 million times the speed of light in a nanosecond. Well, that's just in any amount of time. His rate of speed is 3 million times the speed of light, right?
Yeah, but no, like, that isn't the rate of speed. Like, well, technically. So he walks that amount of, like, he walks 3 million times the speed of light in a nanosecond. Like, in a nanosecond, he walks that amount.
Yeah, but the speed of light is a speed. It's not a distance.
Yeah, but I'm pretty sure, like...
Are you talking about, like, light years?
No, like, Thomas Running invented running in 1874 by trying to... If he walked at 3 million times the speed of light... Oh, yeah, that doesn't make sense. How much would... Yeah, light years. Yeah, sure.
Okay, so
yeah, sure.
You want to change it to light years?
Yeah,
he walks at 3 million light years in a nanosecond?
Yeah, he walked 3 million light years in a nanosecond, sure.
Okay. And you want to know what day it would be when he would have walked 100 googolplex tenths of a kilometer.
Mm-hmm.
Okay, a lot of conversions here. This is a really interesting question. In order to figure it out, I'm not going to be able to do it mentally. After January 14th. And that would be my answer.
Yeah, no.
Today's question of the day is to answer Sebastian's question about the person who invented running. You'll have to go back and watch again to understand the full question. Just remember we're talking about light years, not the speed of light. All right. Name any fraction between 5/6 and 6/7.
5/7? No, that's before. I mean... Oh wait, 5/7 is... Wait a second. I need to write this down. I have a terrible memory. 5, 6, 5, 7. Oh, then like 6/8 or something.
So you're looking for a number that goes right in the middle there. Or not right in the middle, just anywhere between those two.
Yeah.
What's your answer?
Like 6/8 or something?
That's the same as 3/4. That would be to the left of both of those.
Okay. So 5, 6, 5, 7. That's like 2.5 thirds. And like divided by 6, and like 7 thirds, 2 1/3. And 2 1. I don't even know what I'm doing at this point.
Oh, 2 1/3 thirds.
Yeah, so this goes on top, right? No.
No.
Oof. So that means 5/6, 5/7. 5, 6.5. Final answer.
Okay, can you write that as a fraction that doesn't have a decimal in the denominator?
Well, I can try. 0.5, 1.1, and then...
How about one that doesn't have a decimal anywhere?
Okay, I can write a fraction. That's... So that means 50 65th.
Nice. High five. I like it. Just let the record show here. You know, we've got something that's backwards for you.
Yeah, probably.
5. We got some work on the bottom that was scratched out, and then ultimately came out with 5 6.5ths, which he converted to 50 65ths. Nicely done.
I don't know where that took me so long.
Yeah, why are you standing on the chair?
I don't know.
Yeah, me neither. Next question.
Oh wait, there's one more question?
There's one more. Which is more, 3 to the 4th power or 4 to the 3rd power? We'll figure it out.
3 times 3. Imagine it's a trick question. It's like both equals the same value. Like, oh. Yeah.
Which one's bigger?
4 to the 3rd power.
Okay, so between 3 to the 4th and 4 to the 3rd. 4 to the 3rd was bigger.
Yeah.
What you did here is you multiplied 16, 4 times 4, times 4 to get 64.
Yeah.
Times 4 to get 256.
Yeah.
So you did 4 times 4 times 4 times 4. But that asks you to do 4 times 4 times 4.
So that means it's like 64.
Okay.
64, and then, yeah.
So which one's bigger?
3 to the 4th power.
Okay. I'm going to give you another question, and there's a reason I'm giving you this question next.
Okay.
Which one's bigger? 2 to the 5th power?
Or 5 to the 2nd power.
Yeah, okay. You already figured it out.
I've noticed a pattern. 5 times 5, 25.
Hold on. Before you figure it out, which one do you think is going to be bigger? Do you have a prediction?
First one.
Why?
Without a doubt, because 5 times 5 is 25.
Mm-hmm.
Well, I kind of already figured it out beforehand, but the like 2 times 2 times 2 times 2 times 2. It's gonna, yeah.
Okay.
It's going to be larger than 25.
All right. What is it going to be?
2 times 2 times 2 times 2 times 2, 4, 8, 60, 32.
Okay, so which one's bigger? Okay. Now here's a question that I'm going to have you make a prediction for.
Okay.
13 to the 18th or 18 to the 13th? It's not that one. It's not that one. There's that one and that one. What's your prediction?
Probably this one.
Which one?
13 to the 18th power.
Why?
Wait a second. I just realized something.
What's that?
I realized a pattern.
What's the pattern?
So this is 3 to the 4th power, this is 4 to the 3rd power. And that's the difference. 1, 1. 2 to the 5th power. Well, 2 to the 5th power, 5 to the 2nd power. That's 3, 3.
Mm-hmm.
That's 13, 8, 5, 5. So that means I'm pretty sure it's going to be this one based on the pattern. That every single one that has the difference, same as the difference between the whole numbers and the exponent, is that one's been larger.
Is which one's larger?
Wait, no, that one's larger. That one was larger for that one. What?
No, it wasn't. That one was larger.
Oh yeah, then it's probably.
Okay, let me give you some vocabulary. This number here is called the base, and this is called the exponent. Okay, so tell me what you're thinking when you said that you think 13 to the 18th is bigger than 18 to the 13th.
I noticed a pattern of that was larger when the exponents subtract the difference of the exponents were the same as the difference of the wholes.
Okay, and which one?
Bases.
And which one's going to be larger?
I thought that 13 to the 18th power would be larger.
Okay, use the word base and exponent to tell me which one's going to be larger.
The base 13. The base of 13 and the exponent of 18th is going to be larger.
Okay, so here's another one.
Okay.
17.
Wait, did I get that one right?
We'll check it. Should we check it?
Sure.
All right.
Calculator. Or I can solve it right now. Let's see if I can solve it. 130 plus 8 104. It's 134 and 180.
Well, hold on. How are you doing this so quickly? No, you're doing 13 times 18.
Oh, wait.
Yeah.
Never mind.
13 to the 18th equals something times 10 to the 20th. That's exponent or scientific notation. And then 18 to the 13th is something times 10 to the 16th.
So
hey, you were right.
Oh, really?
Okay.
Okay.
17 to the 32nd or 32 to the 17th.
It might be that one because the pattern. But let me try.
So what I'm trying to get you to do is to tell me the pattern in general terms without saying these actual numbers.
Oh, well, the exponents subtracted are the same as the difference of the base, the differences of the base.
Yeah, let me actually make it even simpler for you. When you do 4 minus 3 and 4 minus 3, you get the same, right?
Yeah.
What I'm saying is that the base and the exponents are the same numbers, they're just switched in both of these cases.
Yeah.
So when the base to some exponent and that exponent to the base, if you see it like that, are the same, which one's bigger?
Wait, what? Wait.
How did you know which one was going to be bigger in this case?
I realized that these are flipped, so that means the base with the smaller number is going to be the larger one if these are flipped.
Great. Okay, that's a good way of putting it. So that's a nice conjecture. How could we test that?
By doing 17 to 32nd. 17?
Yeah, and then comparing them, right? Which would take forever. I wonder if it works with all numbers no matter what. Can you try to think of a number, a combination of base and exponent, where that doesn't work?
Probably not, but -1 is third.
Ooh. And what would be the one you're comparing it to?
3 to the -1st.
Mm-hmm. So you're saying which one of those should be bigger according to our rule?
According to our rule, this one should be bigger.
-1 to the 3rd. All right?
Yeah.
So let's test it. This one might actually be easier to do. You just wrote -1. I think you need to do 1 negative.
What?
To the 3rd power.
That doesn't make sense.
Right, that's just how you write -1 on the calculator. So -1 to the 3rd power, and you get -1. Because -1 times -1 is 1, times -1 again is -1. 3 to the -1st power. Let's figure it out. I know what this is. It's clear. 3 to the exponent -1st equals 0.33333. Which one was bigger?
What?
That's not the one you said was going to be bigger.
Who would have thought?
I mean, I just asked you to come up with a counterexample, and you did. So, let me tell you something. Sometimes when you come up with a conjecture, it works for like a certain set of numbers, but not all numbers. So I bet if we reduce this to like maybe all positive numbers, maybe all numbers greater than 1, I don't know, you'd be right. But for some weird cases, like where one of the numbers is less than 1, or maybe where it's less than 0, maybe it breaks down.
Yeah. Cool.
V's up. Both of them. I see both of them. All right. Yeah.
I just did a math I just focused on a math problem without slanting and looking at the teacher.
Heresy. Shut your mouth. All right, see you later, buddy. Thank you.
Later.